The frame opens in stillness, suspended in warm afternoon light. A monarch butterfly drifts across the meadow with an ease that feels almost deliberate, its broad orange wings edged in black tracing slow, confident arcs through the air. Each wing beat is unhurried, the movement less like escape and more like display, as though the insect is aware of the eyes drawn toward it. Against the green of grasses and flowering stems, the pattern is unmistakable. High contrast, saturated color, symmetry sharpened by bold veins. This is the kind of image that invites admiration rather than analysis. A beauty shot meant to disarm the viewer and suggest fragility, lightness, and harmlessness. Yet in ecological terms, nothing about this butterfly is accidental, and nothing about its beauty exists for the sake of being admired. As the camera follows the monarch closer, the illusion of innocence begins to fracture. That brilliant orange is not a flourish of decoration, but a signal, refined over generations by the unforgiving mathematics of survival. In nature, color often carries meaning. And here the meaning is not invitation, but warning. The monarch does not hide among leaves or mimic bark or vanish into shadow. It advertises itself openly, moving slowly enough to be noticed. This is not recklessness. It is confidence rooted in chemistry, a declaration that comes with consequences for those that ignore it. The story of the monarch's defense begins long before it ever takes flight. It starts at ground level, where milkweed plants push their thick leaves toward the sun, exuding a sticky white latex when damaged. For many herbivores, milkweed is a lethal mistake. Its tissues are laced with cardiac glycosides, compounds that interfere with the sodium-potassium pumps essential to animal heart function. In vertebrates, ingestion can cause vomiting, disorientation, and in sufficient quantities, heart failure. To most insects, milkweed is unpalatable or outright toxic. To monarch caterpillars, it is the only acceptable food. When a monarch larva hatches, it begins feeding almost immediately, mandibles scraping leaf tissue in slow, methodical bites. The caterpillar does not neutralize the toxins it ingests. Instead, it sequesters them, storing the compounds within its own tissues as it grows. Over time, the larva becomes a living reservoir of plant poison, carrying forward the chemical defenses of its host into every stage of its development. By the time it pupates and later emerges as a butterfly, those toxins remain embedded within its body, concentrated and ready. The adult monarch does not produce venom, does not sting, does not bite. Its danger lies entirely in consequence. Predators discover this consequence through experience, not instinct. A young bird, newly independent and searching for food, may spot the bright butterfly and interpret it as an easy meal. The monarch offers no dramatic evasion, no sudden burst of speed. It is caught, tasted, and quickly rejected. The toxins do their work almost immediately, triggering nausea and discomfort that the bird will not soon forget. The butterfly may survive the encounter or may not, but the lesson is learned either way. Bright orange wings become associated with sickness, and the predator's behavior changes permanently. In ecological terms, this is education through failure, and it is brutally effective. This dynamic transforms the monarch's coloration into a form of communication, one that operates across species boundaries. The butterfly does not need to attack or threaten. It simply exists, visible and unhidden, allowing its appearance to speak on its behalf. Over time, predators that share the same environment begin to avoid not just monarchs, but any insect that resembles them. This opens the door to mimicry, where unrelated species adopt similar color patterns to borrow the protection earned by the monarch's chemical defense. In this way, the monarch becomes a teacher not just to its enemies, but to the ecosystem itself, shaping visual language across entire communities of insects and birds. The danger the monarch represents is therefore indirect, but profound. It is not an act of aggression, but a delayed consequence, unfolding inside the body of the predator after the choice has already been made. This distinction matters. Aggression requires energy, speed, and risk. Consequence requires only persistence and memory. The monarch's strategy, shifts the burden of survival away from constant vigilance and onto the learning capacity of its predators. Once taught, the lesson sustains itself. This strategy is reinforced by the monarch's physiology and behavior. Unlike many butterflies that dart unpredictably or cling tightly to cover, monarchs often fly at moderate heights and speeds, their wing beats steady and visible from a distance. This is not inefficient flight, it is legible flight. The butterfly wants to be seen, recognized, and categorized correctly. Every successful avoidance by a predator strengthens the signal, reducing future attacks not only on that individual, but on the population as a whole. Yet the monarch's reliance on consequence rather than force introduces its own vulnerabilities. The system only works if predators can learn and remember. Young predators, migrants unfamiliar with the signal, or species with different tolerances to toxins may still pose a threat. This is where scale becomes critical. Monarch populations rely on numbers, repetition, and consistency across landscapes to maintain the integrity of their warning signal. A single butterfly can teach a lesson, but a generation reinforces it. Nowhere is this more evident than during the monarch's migration, one of the most remarkable movements in the insect world. Each year, monarchs travel thousands of kilometers across North America, navigating vast distances without guidance from individuals who have made the journey before. Multiple generations participate in this cycle, with one final generation completing the full migration to overwintering sites. Along the way, the warning colors remain constant, broadcasting the same message to a rotating cast of predators across forests, plains, and agricultural land. At overwintering sites, monarchs cluster in dense roosts, wings folded, bodies layered by the thousands on tree branches. From a distance, the mass resembles dead leaves clinging to bark, but up close, the orange is unmistakable. Even here, during a period of reduced movement and vulnerability, the warning remains visible. Predators approaching the cluster are confronted not with a single signal, but with a wall of it, an overwhelming reminder of past mistakes. The monarch's dependence on milkweed ties its fate tightly to the structure of the landscape. Where milkweed disappears, so too does the chemical foundation of the butterfly's defense. Without access to toxic host plants, caterpillars cannot sequester sufficient compounds, and adults lose the credibility of their warning. Predators do not distinguish between symbolic danger and real danger. If the consequence fades, the signal collapses. In this way, habitat loss does not merely reduce monarch numbers, it erodes the evolutionary contract between appearance and outcome. What emerges from the monarch's story is a form of power that feels counterintuitive. This is not dominance through strength, speed, or aggression, but through honesty. The monarch advertises exactly what it is and allows the world to respond accordingly. Its survival depends not on surprise but on memory, not on attack but on restraint. It transforms vulnerability into leverage by ensuring that harm, once attempted, is never forgotten. The beauty shot, when viewed through this lens, becomes something else entirely. Those glowing wings are not an aesthetic gift to the observer, but a biological statement shaped by selection, chemistry, and the psychology of predators. The monarch does not threaten. It reminds. Its danger is not what it does to you in the moment, but what you carry away afterward, etched into neural pathways and future decisions. In a world where most animals survive by acting, the monarch survives by being understood and by making sure that misunderstanding is costly. The camera settles low to the ground, where sunlight filters through sparse grass and strikes the cracked surface of a stone path. At first glance, the scene feels almost decorative. Small red and black shapes dot the earth like spilled embers, their geometric patterns sharp against the muted browns and greens of soil and leaf litter. The insects move slowly, deliberately, often bumping into one another, sometimes climbing over bodies already at rest. There is no urgency here, no frantic scattering, no attempt at concealment. The firebugs remain fully exposed, gathered in clusters so dense that individual outlines blur into a living mosaic. To an untrained eye, they appear harmless, perhaps even ornamental, as though nature has arranged them for visual effect alone. This impression is exactly the point. Firebugs live at the intersection of visibility and consequence. Their coloration is not subtle, not variable. and not designed to blend with any natural background. The red is saturated, the black sharply defined, arranged in symmetrical patterns that the visual systems of birds and reptiles detect with ease. This is not camouflage, but declaration. Like the monarch butterfly, firebugs use aposematism, a strategy in which bright, contrasting colors advertise an unpleasant truth about the organism displaying them. But where the monarch relies on individual recognition during flight, firebugs amplify their message through numbers. The warning is not whispered by a single body, but shouted by hundreds at once. To understand why this works, it helps to consider how predators learn. A young bird foraging near the ground is bombarded with sensory information, shapes, movements, and colors competing for attention. In this chaos, rarity is often overlooked, but repetition stands out. A single red insect might be tested. A cluster of dozens becomes impossible to ignore. When a predator samples a firebug, the experience is rarely lethal, but it is deeply unpleasant. Firebugs possess chemical defenses derived in part from their plant-based diet, compounds that render them distasteful and difficult to digest. The predator reacts with rejection, sometimes violent, wiping its beak against the ground or shaking its head in discomfort. The crucial detail is that this lesson does not occur in isolation. The predator does not encounter one firebug and move on. It encounters many, all carrying the same visual signature. The association between color and consequence is reinforced repeatedly within minutes. In ecological terms, this is accelerated learning. The firebugs sacrifice nothing extra in this process. Their defense does not require coordinated attack or escape. It requires only presence. Clustering plays a second, less obvious role. By aggregating, firebugs reduce the risk to any single individual. If a predator targets the group, only a small fraction are actually sampled, while the majority benefit from the lesson learned at another's expense. This dynamic, sometimes referred to as the dilution effect, shifts the cost of predation away from individuals and distributes it across the population. The cluster becomes both a shield and a signal, increasing survival odds not by hiding members, but by ensuring they are remembered. The environment in which firebugs thrive reinforces this strategy. They are often found in open, sunlit areas near trees, especially around the bases of trunks where seeds accumulate. These spaces are visually exposed, lacking the dense cover that might favor camouflage. Instead of fighting the conditions, firebugs lean into them. Their slow movement and high visibility are not weaknesses here, but assets. Against bare soil and pale bark, the red and black pattern becomes even more striking, transforming the ground itself into a stage. This visibility also intersects with thermoregulation. Dark pigments absorb heat, and firebugs use this to their advantage, especially in cooler climates or early in the season. By clustering, they create small pockets of retained warmth, allowing their bodies to reach functional temperatures more efficiently. The same grouping that amplifies their warning signal also stabilizes their internal physiology. Heat absorbed by one individual radiates outward, benefiting neighbors and reducing the energetic cost of maintaining activity. The cluster is therefore not just a billboard, but a thermal engine, driven by sunlight and shared space. As the camera moves closer, individual behaviors emerge. Some firebugs remain motionless, legs tucked beneath their bodies conserving energy. Others climb slowly over the mass, navigating by touch and chemical cues rather than sight. Pairs are often seen joined end to end in prolonged mating, a posture that further emphasizes their lack of fear. Even during reproduction, one of the most vulnerable moments in an insect's life, firebugs do not retreat into secrecy. They remain in the open, their warning colors uninterrupted by the demands of survival. This confidence rests on consistency. Aposematic signaling only works if the signal is honest across time and space. If predators occasionally encounter palatable insects wearing the same colors, the message weakens. Firebugs maintain signal integrity through both chemistry and behavior. Their diet, often based on seeds from specific plants, supports the production and retention of defensive compounds. Their clustering ensures that predators rarely encounter a single ambiguous case. The result is a stable visual language that predators learn quickly and abandon reluctantly. There is an irony here that borders on elegance. In many ecosystems, small insects survive by avoiding attention altogether. Firebugs survive by monopolizing it. They turn themselves into landmarks, predictable and unmistakable. This predictability, often a liability, becomes their strength. Predators that learn to ignore firebugs save time and energy, focusing instead on prey that offers real nutritional return. Over generations, this mutual understanding settles into the background rhythm of the ecosystem. Firebugs persist, predators adapt, neither side escalates. Yet this system is not without fragility. The firebug's reliance on group signaling means isolation carries risk. A lone individual, separated from the cluster, loses the amplifying effect of repetition. Its colors still warn, but the message is quieter, easier to test. This is why firebugs are rarely seen alone for long. Movement across the landscape tends to be short and purposeful, often ending where others are already gathered. Chemical cues help guide this process, allowing individuals to locate suitable aggregation sites and maintain the integrity of the signal. The broader ecological impact of this strategy extends beyond predator avoidance. By feeding on fallen seeds, firebugs influence plant regeneration patterns, subtly shaping the composition of the habitats they occupy. Their presence near specific tree species reflects not just dietary preference, but co-evolutionary relationships between plant chemistry and insect tolerance. The same compounds that deter many herbivores become manageable, even useful to firebugs, reinforcing the link between food choice and defense. From a human perspective, it is tempting to interpret the firebug's appearance as decorative or benign. Their slow pace and lack of obvious weaponry invite underestimation. But in ecological terms, they are highly optimized communicators, broadcasting a message honed by countless failed attacks. The beauty is not incidental, it is functional, purposeful, and unforgiving of misinterpretation. As the scene widens, the cluster remains, a patch of living color against the earth. Birds pass overhead without descending. Lizards pause at the edge of the group, then move on. The firebugs do not react. They continue basking, feeding, mating, their presence uninterrupted. The warning has been received and accepted. In this quiet standoff, no violence is necessary. The billboard has done its job. The lesson carried by firebugs is subtle but profound. Survival does not always depend on speed, stealth, or strength. Sometimes it depends on clarity. By making themselves impossible to ignore, firebugs ensure that predators make better choices next time. Their brilliance is not an invitation but a boundary, drawn in color and reinforced through memory. In the calculus of evolution, this is efficiency at its most refined, a strategy where being seen is safer than being hidden, and where beauty is simply the visible surface of a very serious message. The scene opens in harsh, open light, the kind that leaves little room for concealment. Cotton fields stretch outward in ordered rows, their pale leaves and drying boles reflecting the sun. On the stems and seed pods, flashes of red move slowly, deliberately, refusing to disappear even when the camera draws close. The red cotton bug does not hide in shadow or retreat beneath foliage. It remains in plain view, its crimson body sharply outlined against white cotton fiber and dusty green leaves. The contrast is striking, almost confrontational, as though the insect has chosen visibility over safety and decided to make that choice work. At first glance, the red cotton bug looks like an obvious target. It is not fast, its movements are measured, almost casual, as it probes plant tissue with a slender beak adapted for piercing and sucking. There is no armor, no spines, no explosive escape response. For a predator scanning the field, this insect appears to offer an easy meal. And yet, in ecosystems where red cotton bugs are common, predators learn quickly that this impression is misleading. The danger posed by this insect does not manifest as pain or paralysis, but as disappointment and discomfort, repeated often enough to reshape behavior. The red cotton bug feeds primarily on seeds, including those of cotton plants, drawing nutrients directly from developing kernels. This diet is chemically complex. Cotton seeds contain compounds that are difficult to process and, in some cases, toxic to animals not adapted to them. As the bug feeds, it incorporates these substances into its own tissues, becoming distasteful and energetically unrewarding to consume. To a predator, the red cotton bug is not deadly, but it is inefficient prey. The cost of eating it exceeds the benefit. This imbalance is critical. In predator decision-making, food is evaluated not only by availability, but by profitability. A prey item that requires handling time, induces nausea, or provides little nutritional return becomes a poor investment. The red cotton bug exploits this logic by making its unprofitability obvious. Its coloration is not subtle warning but overt announcement. The red is vivid, saturated, and consistent across individuals and life stages, creating a visual shorthand that predators learn to associate with a bad outcome. The learning process unfolds through experience. A bird may capture a red cotton bug and swallow it, only to encounter digestive discomfort or an unpleasant taste that lingers. The predator survives the encounter, but the memory remains. Unlike venomous prey, which can deter through immediate pain, the red cotton bug relies on delayed feedback. The predator is not punished at the moment of attack, but afterward, when the decision cannot be undone. This timing makes the lesson particularly durable. The predator does not simply avoid the bug because it hurt. It avoids it because it was not worth the effort. Over time, this experience-based avoidance becomes ingrained. Predators begin to bypass red shapes altogether, even when hunger pressures increase. The red cotton bug's success depends on this reliability. Its signal must be honest. If too many individuals were palatable, the system would collapse. Instead, chemical consistency across the population ensures that the warning remains credible, reinforced each time a predator makes the wrong choice. Visibility is essential to this strategy. The red cotton bug does not attempt to blend into cotton plants, despite living on them. Instead, it positions itself where contrast is maximized, often congregating on exposed seed pods or stems. In doing so, it increases the likelihood of being seen and recognized before an attack occurs. This preemptive recognition reduces the number of encounters that reach the testing stage. Predators that have already learned the lesson simply move on, conserving energy and avoiding discomfort. Aggregation further amplifies this effect. Red cotton bugs are often found in groups, their combined coloration forming large patches of red that dominate the visual field. For predators, this repetition accelerates learning. A single unpleasant experience is reinforced by the sight of many identical signals. The environment becomes saturated with reminders. The bug's body becomes part of a larger pattern, a warning distributed across space rather than confined to an individual. There is also a physiological dimension to this clustering. Like many insects, red cotton bugs rely on external heat sources to regulate body temperature. By basking in sunlight together, they warm more efficiently, reaching activity thresholds sooner in the day. The dark elements of their coloration absorb heat, while the red surfaces help maintain visibility. Thermoregulation and signaling converge in a single design, reducing the need for compromise. The bug does not choose between warmth and warning. It achieves both simultaneously. From the predator's perspective, the red cotton bug becomes background knowledge, a rule rather than a choice. This changes the dynamics of the ecosystem. Predators that avoid these bugs redirect their foraging toward other species, increasing pressure elsewhere. In this way, the red cotton bug strategy has ripple effects, influencing not only its own survival, but the distribution of predation across the community. Its presence shapes behavior beyond its immediate interactions. The red cotton bug's relationship with cotton plants adds another layer of complexity. While the insect is often labeled a pest due to its impact on seed quality, its ecological role is more nuanced. By feeding on seeds, it influences plant reproduction and resource allocation. The chemicals it sequesters originate in the plant's own defenses, turning agricultural chemistry into ecological currency. The bug does not invent its toxicity. It borrows and repurposes it, demonstrating how plant and insect evolution intertwine. This borrowing reinforces the honesty of the warning signal. The red cotton bug cannot fake unprofitability. Its defense is metabolically linked to its diet and physiology. Predators testing the signal receive consistent feedback, strengthening avoidance over time. This consistency is what allows visibility to become protection. In a landscape crowded with moving shapes, clarity becomes safer than ambiguity. There is a subtle irony in this arrangement. The red cotton bug's success depends on predators being intelligent enough to learn from mistakes. In environments where learning is impaired or where novel predators are introduced, the system can falter. Young predators must be taught anew, and some individuals are lost in the process. Yet over generations, the balance holds. The population survives not by eliminating risk, but by managing it, distributing the cost of education across time. As the camera lingers on a group of red cotton bugs clustered along a cotton boll, the field around them remains active. Birds pass overhead, insects dart between plants, the wind moves through leaves. The bugs remain, exposed and unhurried. They do not react to shadows or vibrations unless directly disturbed. Their confidence is not arrogance, but calculation, the product of evolutionary accounting that has determined this strategy to be sufficient. The brilliance of the red cotton bug lies in its refusal to play the usual game. It does not chase safety through concealment or speed. It does not escalate into aggression. Instead, it invests in being remembered. Its danger exists not in what it can do to a predator, but in what it teaches that predator about wasted effort. In ecosystems governed by energy budgets and learned behavior, this is a powerful position to occupy. When the scene finally pulls back, the red dots remain scattered across the pale field, unmistakable even from a distance. They are not ornaments or accidents of color. They are signals, honed by selection and reinforced by experience. The red cotton bug survives because it is genuinely not worth eating, and because it ensures that predators understand this fact as clearly as possible. In a world where most prey rely on not being noticed, this insect survives by making sure it never is ignored. The forest canopy filters sunlight into fragments, breaking the day into shifting coins of brightness and shadow. Leaves overlap, sway, and briefly align before drifting apart again, turning the air beneath them into a restless mosaic. In this unstable light, movement becomes difficult to interpret. Edges blur, shapes dissolve. Against this background, a butterfly settles on a low branch, wings folded, body still. The leopard lacewing looks delicate, almost ornamental, its wings edged with scalloped curves and marked with pale spots and soft gradients. Nothing about its posture suggests urgency or defense. It does not flee when the camera closes in. It does not advertise danger. Instead, it vanishes without moving. The disappearance is not physical, but perceptual. The leopard lacewing remains exactly where it is, yet its outline fractures into the surrounding light. The eye searches for a boundary and fails to find one. This is not camouflage in the traditional sense of matching a background color. The butterfly does not resemble bark or leaf or lichen. Instead, it exploits the way visual systems identify objects, disrupting the process before recognition can complete. The lacewing survives not by being unseen, but by being unreadable. Predators rely on edge detection to locate prey. Whether bird, lizard, or insect hunter, the first step in targeting is locking onto a continuous outline that separates prey from background. In environments where light is uniform, this task is straightforward. In forests, it becomes far more complex. Dappled light fractures contrast, creating false edges and fleeting highlights. The leopard lacewing's wing pattern is tuned precisely to this chaos. Pale spots echo sunflecks, dark patches mimic shadow gaps. Curved lines dissolve into leaf edges and vein patterns. When the butterfly rests with wings closed, its body becomes a collage of familiar fragments rather than a single object. This disruption operates at the level of perception rather than chemistry or strength. The lacewing does not need toxins or speed. It needs time, often measured in fractions of a second. If a predator cannot assemble a coherent target quickly enough, the opportunity passes. The prey remains unharmed, not because it was ignored, but because it was never fully perceived as prey at all. The forest rewards this strategy. Unlike open fields or uniform backgrounds, woodland habitats constantly rearrange their visual structure. Wind moves leaves. Clouds shift overhead. Light pulses and fades. In such conditions, high-contrast warning signals would stand out dangerously. The leopard lacewing takes the opposite approach, embracing complexity and ambiguity. Its patterning is not symmetrical in the way aposematic insects often are. Instead, it is irregular, layered, and noisy. Each wing carries information that resists simplification. When the butterfly does take flight, the illusion breaks briefly. The upper wings flash with richer colors, movement drawing attention. But even then, the flight is not explosive or erratic. It is measured, often short, ending quickly in another patch of broken light. As soon as the wings fold, the pattern resets. The predator's pursuit, if initiated at all, loses coherence. Without a stable outline to track, motion becomes guesswork. This inability to lock on has deep consequences for predator behavior. Chasing prey requires commitment. Energy must be invested, focus maintained. If the visual signal degrades mid-pursuit, the predator faces a decision: continue chasing something that may not exist, or disengage and search for a clearer target. In ecosystems where energy efficiency determines survival, ambiguity favors the prey. The leopard lacewing does not need to outrun danger. It needs only to make danger uncertain. There is a physiological cost to this strategy. Producing complex wing patterns requires precise developmental control. Pigment deposition, scale structure, and wing membrane thickness must align to create the desired visual effect. This is not random decoration, but engineered disruption. Natural selection has favored individuals whose patterns best interfere with predator perception, generation after generation, refining the balance between visibility during flight and invisibility at rest. The lacewing's behavior complements its appearance. It chooses resting sites where light is most fragmented, often near leaf clusters or branching intersections. It aligns its wings to maximize overlap with background patterns, angling itself so that major markings coincide with veins or shadows. These micro-positioning choices matter. A slight shift in angle can determine whether the pattern blends seamlessly or snaps into focus. The butterfly's stillness is therefore active, a form of behavioral precision that completes the visual illusion. Unlike warning-colored insects, the leopard lacewing does not teach predators through experience. There is no unpleasant consequence to sampling it, no toxin to reinforce memory. Its defense works precisely because predators rarely reach the sampling stage. The encounter ends before contact, often before conscious recognition. This creates a different ecological relationship. Predators do not learn to avoid lacewing specifically. Instead, they learn to favor certainty. Prey that is obvious, trackable, and energetically predictable becomes the default target. In this way, the lacewing benefits from the presence of other insects. Brightly colored species draw attention and absorb predation pressure. Cryptic species like the lacewing slip through the gaps created by selective focus. The forest becomes a layered battlefield where different strategies coexist, each exploiting a different weakness in predator perception. There is also a temporal dimension to this survival mechanism. The lacewing is most active during periods when light conditions are variable, early morning and late afternoon when shadows stretch and overlap. During these times, its patterning performs at peak effectiveness. At midday, when light becomes harsher and more uniform, the butterfly reduces activity, resting deeper in foliage where contrast remains broken. Behavior and pattern remain synchronized, reinforcing one another. From the predator's perspective, the forest is full of false positives. Leaves flicker like wings, spots of light pulse like movement. In this environment, the cost of chasing the wrong thing is high. Over time, predators become conservative, favoring targets that present clear, continuous outlines. The leopard lacewing exploits this conservatism. Its pattern ensures that even when seen, it is not trusted. This form of defense reveals an underappreciated truth about survival. Not all danger is avoided by being stronger or more toxic. Some is avoided by exploiting the limitations of perception itself. Vision is powerful but imperfect. It evolved to detect patterns that usually matter, not to resolve every ambiguity. The lacewing thrives in the margins of this imperfection. There is a quiet irony in the butterfly's appearance. To human observers, the leopard lacewing appears striking, even beautiful. We perceive its pattern as decorative because our visual systems are tuned differently, seeking symmetry and novelty. For predators, the same pattern dissolves into noise. Beauty in this context is a byproduct, not a goal. The butterfly's wings are not meant to be admired, only misunderstood. As the camera pulls back, the branch appears empty again. The lacewing remains, wings closed, pattern aligned with shadow and leaf. Nothing marks its presence except the faint suggestion of shape that never quite resolves. In a forest built on fragments, this is the safest form a body can take. The leopard lacewing survives because it denies predators the most basic requirement of an attack: certainty. It does not warn, threaten, or flee. It erases itself at the moment recognition should occur. In doing so, It demonstrates that disappearance is not always about blending in, but about breaking the rules by which vision assigns meaning. Where predators hunt by locking on, the lacewing endures by never letting that lock engage. The forest floor is dim even at midday, a place where light arrives late and leaves early. Trunks rise like columns, their bases lost in shadow, while broad leaves filter the sun into thin, wavering bands. In this subdued world, movement is often detected before form, a flicker of motion registering long before shape or identity. Near the ground, a large butterfly settles against a fallen leaf, wings closed, body angled slightly toward the darkness beneath the canopy. For a moment, it appears inert, another fragment of forest debris. Then the pattern resolves, and the illusion shifts violently in the opposite direction. What fills the frame is not an insect, but a face. Two enormous circular markings dominate the butterfly's folded wings, dark centers surrounded by lighter rings, positioned with unsettling precision. They stare outward, unblinking, symmetrical, and unmistakably eye-like. The owl butterfly does not merely resemble something larger. It evokes something specific. A predator that hunts by sight, a watcher in the shadows. In that instant, the forest rewrites its own logic. Prey becomes threat, beauty becomes alarm. The owl butterfly's strategy is not about concealment or chemical defense. It is about manipulation of fear. Eye spots function by exploiting deeply ingrained biases in predator perception. Many animals, especially birds and small mammals, are hardwired to respond to eye patterns. Eyes signal agency, awareness, and danger. They imply that the observed is not alone, not unaware, and not defenseless. When a predator encounters eyes in the undergrowth, hesitation follows. That hesitation, even when brief, can determine survival. Unlike true predators, the owl butterfly does not pursue or attack. Its eye spots do not belong to a nervous system or direct attention. They are patterns printed on tissue, inert and unseeing. Yet to a predator relying on rapid decision-making, the distinction matters little. The visual system reacts before analysis can catch up. The cost of misjudgment is too high. If those eyes belong to a real predator, approaching could be fatal. The safer choice is retreat. This is the power of intimidation through resemblance. The owl butterfly's eye spots are not random circles. Their size, contrast, and placement are tuned to match the viewing angle of common predators. Positioned low on the wings, they face outward when the butterfly rests, aligning with the line of sight of birds scanning the forest floor. The surrounding rings create depth, mimicking the sclera and iris of vertebrate eyes. Even subtle asymmetries add realism, preventing the pattern from appearing artificial or repetitive. The effect intensifies when the butterfly moves. If disturbed, the owl butterfly may suddenly flash its wings open and closed, revealing and concealing the eye spots in rapid succession. This movement transforms static pattern into apparent behavior, as though the eyes themselves are shifting or blinking. For a predator already on edge, this escalation reinforces the illusion of a living, responsive threat. The butterfly does not flee immediately. It stands its ground just long enough to let fear do the work. This strategy relies on proximity. Eye spots are most effective at close range, where detail matters and reaction time is short. The owl butterfly therefore spends much of its life near the forest floor, flying low and settling among leaf litter where encounters occur suddenly. In open sky, the illusion would fail. On the ground, amid shadows and partial views, it thrives. The butterfly's coloration supports this dual role. The upper wings, visible during flight, are often vivid, drawing attention and allowing the insect to navigate the forest visually. When at rest, the underside dominates, darker and more subdued except for the eye spots. This shift allows the butterfly to alternate between mobility and intimidation, each mode optimized for a different moment in the encounter. The transformation is seamless, requiring no conscious control, only posture. Predators that encounter owl butterflies rarely test the illusion. The point is not to prove the eyes are real, but to avoid the risk of being wrong. Over time, predators may learn that some eye patterns do not correspond to actual threats. Yet the learning process is slow and incomplete. The forest is crowded with real eyes belonging to snakes, birds, and mammals. Discriminating between genuine and false signals under pressure is difficult. The owl butterfly benefits from this uncertainty, hiding within a broader landscape of fear. There is also a misdirection element to the eye spots. Even if a predator chooses to attack, the focus may shift away from the butterfly's body toward the false eyes. Strikes aimed at the wings are far less likely to be fatal than those targeting the thorax. A torn wing can heal or be compensated for. A damaged body cannot. In this way, the eye spots serve as decoys, redirecting violence toward expendable tissue. Survival does not require perfection, only continuation. The ecological context reinforces the effectiveness of this design. In dense forests, predators often operate under low visibility, making snap judgments based on partial information. The owl butterfly's eye spots provide just enough information to trigger avoidance without inviting closer inspection. The pattern does not need to be flawless. It needs to be convincing for a fraction of a second. There is a physiological cost to producing such large wings and complex patterns. The owl butterfly is heavier and less agile than many smaller species. Its flight is slower, more deliberate, making it potentially vulnerable in open spaces. This trade-off makes sense only because the intimidation strategy compensates for reduced escape performance. Evolution has balanced these factors, shaping an insect that invests in psychological defense rather than physical evasion. The forest, in turn, accommodates this specialization. Leaf litter provides resting sites. Shadows provide contrast. Predators provide selective pressure. The owl butterfly occupies a niche where fear is as valuable as speed. Its presence influences predator behavior, adding another layer to the forest's web of signals and counter-signals. Real predators benefit too, as their visual signatures become more potent when echoed by harmless mimics. The boundary between hunter and non-hunter blurs, reinforcing the overall climate of caution. From a human perspective, the owl butterfly's wings are often admired for their artistry. The eye spots are photographed, studied, and celebrated as examples of natural design. But in the forest, they are not art. They are warnings, shaped by countless encounters where hesitation meant survival. The beauty we perceive is incidental, a side effect of a pattern built to manipulate fear. As the camera lingers, the butterfly remains still. The eyes stare back, filling the frame, dominating the scene. Then, slowly the wings open. The face dissolves, and the insect lifts into the dim air, leaving behind nothing but disturbed leaves and a lingering sense of having been watched. The forest resets, the illusion complete. The owl butterfly survives by turning perception against itself. It does not poison, outrun, or disappear. It confronts predators with a question they cannot afford to answer incorrectly. Are those eyes real? In that moment of doubt, fear takes over, and the butterfly lives on. Here, beauty is not decoration, it is a trigger, a carefully tuned alarm that transforms fragile tissue into something that feels dangerous. In the quiet calculus of the forest, that feeling is enough. The sound arrives before the insect does. It begins as a low vibration in the air, a trembling that seems to come from everywhere at once, filling the spaces between trees and seeping into the ground itself. As the camera moves through the forest, the source becomes clearer, but no less overwhelming. Thousands of cicadas cling to trunks and branches, their bodies pressed against bark, their wings vibrating so rapidly they blur into translucence. The forest is no longer quiet or even merely loud. It is saturated with sound, a continuous wall of noise that drowns out birdsong, wind, and the subtle movements of leaves. In this moment, the ecosystem feels transformed, reshaped by a single biological phenomenon that prioritizes intensity over subtlety. Cicadas are not venomous. They do not sting, bite, or inject toxins. They carry no chemical warning and display no intimidating coloration meant to signal danger. Individually, they are slow, clumsy flyers, easily caught by birds, mammals, or reptiles. By conventional standards, they are vulnerable prey. Yet when cicadas emerge en masse, vulnerability becomes irrelevant. Survival no longer depends on avoiding predators one by one. It depends on overwhelming the environment so completely that predation loses its efficiency. The foundation of this strategy is time. Cicadas spend the majority of their lives underground as nymphs, feeding silently on the xylem fluids of plant roots. This subterranean existence can last for many years, sometimes more than a decade, during which the insects remain largely invisible to the world above. Their development is slow, constrained by the low nutritional value of their diet. But this slowness is not a weakness, it is preparation. Beneath the soil, entire populations grow in synchrony, waiting for environmental cues that signal the moment to surface. When that moment arrives, it does so with startling precision. Soil temperature rises to a specific threshold, and almost overnight, the ground erupts with life. Nymphs crawl upward, emerging in numbers so vast they carpet tree trunks and fence posts. They climb, anchor themselves, and molt, splitting their exoskeletons to reveal winged adults. The forest fills with the brittle shells of abandoned skins, evidence of transformation on a massive scale. This emergence is not staggered or cautious. It is explosive, compressing years of development into a brief window of visibility. Predators respond immediately. Birds gather. Mammals investigate. Reptiles bask and wait. The sudden abundance of food is impossible to ignore. And yet, despite intense predation, cicada populations persist. The reason lies not in resistance, but in arithmetic. There are simply too many cicadas to be eaten. Predators become satiated long before they can make a meaningful dent in the population. The excess survives by default. This is survival by overload, a strategy that turns numerical disadvantage into ecological dominance. Sound plays a crucial role in reinforcing this effect. Male cicadas produce some of the loudest biological sounds in the insect world, generated by specialized structures called tymbals on their abdomens. These membranes buckle and snap back at high speed, creating rapid pulses that combine into a sustained chorus. The volume can reach levels comparable to industrial machinery, enough to cause discomfort in human listeners standing nearby. For predators, the effect is more than annoyance. It is sensory disruption. In a sound-saturated environment, auditory localization becomes difficult. Predators that rely on hearing to detect movement or pinpoint prey struggle to isolate individual targets. The chorus blurs spatial cues, turning precise signals into a uniform roar. Even visually oriented hunters are affected. Sound influences attention. When everything vibrates and pulses, the brain prioritizes escape and orientation over fine targeting. The cicadas do not need to hide. They flood the sensory field until discrimination fails. This sonic intensity also interferes with communication among predators. Alarm calls, territorial signals, and contact calls are masked or distorted. The forest's usual acoustic hierarchy collapses under the weight of the cicada chorus. For a brief period, cicadas become the dominant signal, reshaping how information flows through the ecosystem. The danger they pose is not physical harm, but informational overload. There is an irony in this dominance. The sound exists primarily for reproduction, not defense. Males call to attract females, each species producing a distinct pattern that allows individuals to find suitable mates amid the noise. Females respond by flicking their wings, creating subtle sounds that guide males closer. This exchange occurs within the broader roar, a fine-tuned conversation layered atop chaos. What benefits reproduction also benefits survival, a coincidence that evolution has preserved and amplified. Predators that continue hunting during an emergence adopt opportunistic strategies. They strike randomly, capturing what they can without discrimination. Precision hunting becomes inefficient. This randomness further protects cicadas, as individual risk decreases when attacks are unguided. Even unsuccessful strikes cost predators energy, while the abundance ensures the prey population absorbs the losses. The temporal limitation of the emergence is equally important. Cicadas do not linger. Adults live for a short span, focused almost entirely on reproduction. They do not disperse widely or attempt to colonize new areas during this phase. Their goal is not long-term presence, but immediate success. Eggs are laid in plant tissue, and soon after, adults die, their bodies falling to the forest floor where they become a pulse of nutrients, enriching the soil that will support future generations. This nutrient influx has cascading effects. Plants benefit from increased nitrogen. Microbial activity spikes. Other insects respond to the temporary abundance of decaying organic matter. The cicada emergence is not just a spectacle, but an ecological event, altering resource availability across trophic levels. Predators that gorge on cicadas experience short-term population boosts, influencing dynamics long after the sound has faded. From an evolutionary perspective, the cicada's strategy reveals an alternative path to safety. Instead of avoiding predators, cicadas accommodate them. Predation is expected, absorbed, and rendered inconsequential by scale. The insects do not evolve sharper defenses because they do not need to. Their protection lies in synchronization and excess. Even the cicada's clumsy flight reflects this logic. Agile flight would require energy and specialized musculature. Cicadas invest instead in sound production and reproductive output. Their bodies are optimized for calling, their thorax is packed with muscles dedicated to vibration rather than maneuverability. When a cicada is caught mid-flight, it is not a failure of design, but an accepted cost. As the chorus reaches its peak, the forest feels almost unreal. The air hums, the ground vibrates faintly. The usual hierarchy of sounds is erased. For predators and observers alike, the environment becomes less navigable, less interpretable. Targeting becomes guesswork. In this altered state, the cicadas thrive. Eventually, the sound begins to thin. Individuals fall silent. Predators move on. The forest slowly reclaims its acoustic space. What remains are the shells, the eggs hidden in twigs, and the soil enriched by decay. Beneath the surface, the next generation begins its long, quiet development, invisible once more. The cicada's danger was never venom or aggression. It was presence at scale, amplified through sound. By transforming the environment into something too loud, too crowded, and too overwhelming to pass, cicadas ensure that no predator can focus long enough to eliminate them. Their survival is not about being untouchable. It is about being unignorable, and in that excess, untargetable. The air above a summer meadow shimmers with heat, the kind that softens edges and makes distance feel elastic. Flowers stand open and still, their colors saturated by sunlight, nectar pooling deep within tubular blooms. Then something arrives that seems out of scale with the insects around it. A compact body snaps into view, suspended in mid-air, wings beating so fast they dissolve into a transparent blur. For a moment, it could be mistaken for a bird, or even a mechanical device, hovering with improbable stability before darting sideways without warning. This is the hummingbird Hawk-moth, an insect that turns motion itself into a form of defense. At rest, which it rarely allows itself, the moth is unassuming, its wings folded tight against a stout body patterned in muted browns and grays. In motion, it becomes something else entirely. The wings accelerate to an extraordinary frequency, generating lift without forward movement, allowing the moth to hover precisely in front of a flower while extending a long proboscis deep into the bloom. The body remains nearly stationary, yet the wings carve invisible arcs through the air, producing a faint hum that hints at the energy being expended. This ability to hover is not an ornament or a curiosity. It is the foundation of a survival strategy built on speed, control, and unpredictability. Hovering flight is rare among insects because it demands constant power output and fine-scale muscular control. The hummingbird Hawk-moth achieves this through a thorax densely packed with flight muscles and a wing structure optimized for rapid oscillation. Unlike many butterflies and moths that rely on gliding phases between wing beats, this species maintains continuous motion, adjusting angle and stroke in real time to counter turbulence and gravity. The result is flight that resembles that of a hovering bird more than a typical insect, a convergence driven by shared physical constraints rather than shared ancestry. For predators, this creates an immediate problem. Many insect hunters rely on predicting trajectories, calculating where prey will be a moment in the future. The hawk-moth undermines this by refusing to commit to linear motion. It can stop, reverse, or sidestep in fractions of a second, changing direction without decelerating. What looks smooth to a human observer is, in practice, a series of micro-adjustments that keep the moth perpetually just out of reach. The meadow becomes a three-dimensional maze when viewed from the perspective of a predator. Flowers act as both resources and obstacles. The hawk-moth weaves between them, hovering at one bloom, then snapping to the next with a burst of acceleration. Each movement is precise but not repetitive. The pattern never settles long enough to be learned. This variability is critical. If the moth followed predictable paths, predators could adapt. Instead, every feeding bout is slightly different, forcing hunters to start from zero each time. The moth's appearance amplifies this confusion. Its body is compact and robust, while its wings blur into near invisibility at speed. Predators attempting to focus on a clear outline are presented with a paradox. The moth is clearly present, audible even, yet visually unstable. The eye struggles to track what the brain cannot anchor. Motion smears edges. Wing beats erase boundaries. The insect becomes more event than object. This sensory disruption is compounded by the moth's coloration. While perched, its tones blend with bark and stone. In flight, flashes of warmer hues appear and vanish, too brief to resolve into a stable signal. There is no warning pattern to learn, no obvious marker to avoid. Instead, predators encounter a moving target that defies categorization. It is not slow enough to be typical prey, not large enough to be a bird, and not patterned enough to suggest toxicity. The safest response is hesitation. Hesitation is all the hummingbird hawk-moth needs. Its feeding strategy requires prolonged exposure. Hovering in front of a flower leaves it vulnerable if predators could strike accurately. Speed alone would not suffice without control. The moth must maintain position with centimeter-level precision, compensating for wind and its own wing turbulence. This control allows it to feed efficiently while remaining ready to escape instantly. Escape, when it comes, is not a straight line. The moth rarely flees directly away from danger. Instead, it performs abrupt lateral movements, zigzagging through space in a way that breaks pursuit. Predators that lunge find themselves grasping empty air, their momentum carrying them past the point where the moth had been only a moment earlier. Each failed attempt reinforces the difficulty of capture, reducing future effort. There is a metabolic cost to this lifestyle. Hovering flight consumes enormous amounts of energy. The moth must feed frequently, its nectar intake fueling both flight and the heat generated by constant muscle activity. Thermoregulation becomes a balancing act. The rapid wing beats produce warmth, allowing the moth to remain active even in cooler conditions, but overheating is a risk under intense sun. Behavioral adjustments solve this problem. The moth alternates between feeding bursts and brief rests in shade, managing body temperature through movement rather than physiology alone. This capacity for sustained activity expands the moth's ecological window. It can forage during times when other insects are sluggish, reducing competition. Early mornings and cooler evenings become opportunities rather than constraints. Predators too are affected. Hunters adapted to peak daylight conditions may be less efficient during these periods, further tilting the balance in the moth's favor. The hawk-moth's migration adds another layer to its strategy. Some populations travel long distances, crossing regions in search of flowering plants. During these journeys, the same flight capabilities that frustrate predators also allow the moth to navigate complex air currents and landscapes. Speed and endurance combine, enabling rapid colonization of new habitats. For predators unfamiliar with the moth's behavior, encounters are even less successful. Novel prey that behaves unpredictably is often ignored in favor of known targets. The relationship between beauty and confusion becomes clear at close range. To human eyes, the hummingbird hawk-moth appears jewel-like in motion, a living ornament hovering effortlessly among flowers. That impression arises because we interpret control as elegance. For predators, the same control reads as chaos. The moth's movements violate expectations built on experience with other insects. Beauty in this context is not coloration alone, but the smoothness of impossible motion, a visual spectacle that conceals a highly practical function. There is a subtle irony here. The moth's resemblance to a hummingbird may provide incidental protection. Predators accustomed to avoiding birds might hesitate when confronted with something that behaves like one, even if it is far smaller. The resemblance is not perfect, but it does not need to be. Confusion thrives on ambiguity. The moth occupies a perceptual gray zone where certainty is impossible. As the camera follows the hawk-moth from flower to flower, the meadow feels different. Space seems compressed by rapid movement, expanded by sudden stops. The insect never truly settles into the frame, always threatening to escape it. When it finally darts upward and vanishes beyond the flowers, the air it occupied feels momentarily empty, as though something mechanical has powered down. The hummingbird hawk-moth survives not by being untouchable, but by being untrackable. Its danger lies in speed married to control, in motion that refuses to resolve into something a predator can calculate. Beauty here is not passive. It is kinetic, born of muscles, physics, and constant adjustment. In a world where many prey depend on hiding or warning, this moth chooses neither. It lives in the open air, daring predators to try, and wins by turning every encounter into a puzzle they cannot solve. The leaf trembles slightly under the weight of something solid, something that does not belong to the fragile world of lace wings and brittle antennae. A shieldbug sits exposed on the upper surface, its body broad and flattened, edges clean and geometric, as though cut from polished enamel. Light slides across its back and breaks into reflections of green, bronze, and copper, colors that seem almost manufactured rather than grown. The insect does not rush to hide. It does not fold itself into shadow. It remains where it is, fully visible, its outline unmistakable against the leaf. This is not a creature built for vanishing. It is built to be noticed. The shieldbug's appearance suggests protection even before it acts. Its exoskeleton is thick and domed, forming a continuous shield that covers wings, abdomen, and vital organs beneath a single armored plate. This structure deflects minor attacks and resists casual bites. But armor alone is rarely enough in the insect world. Many predators can pierce, crush, or pry apart even well-protected prey. The shieldbug's true defense lies not in what it can withstand, but in what it can release. When threatened, the transformation is immediate and unmistakable. From small openings along its body, the shieldbug emits a fine mist, a visible spray that disperses outward in a short, directed burst. To the camera, the cloud catches the light like vapor, a brief shimmer in the air before dissipating. To a predator, it is a chemical ambush. The spray carries a potent mixture of volatile compounds, sharp and acrid, designed to overwhelm sensory systems rather than cause physical injury. The attack is not subtle. It is meant to be experienced fully and remembered. This is not venom delivered through a wound. It is defense through exposure. The chemicals irritate eyes, nasal passages, and mouth, triggering immediate aversion. Birds recoil, shaking their heads violently. Small mammals retreat, rubbing their snouts against the ground. Even predators that do not rely heavily on smell react to the sudden sensory assault. The shieldbug does not need to flee while this happens. The moment of contact is enough. The effectiveness of this strategy depends on learning. The first encounter may end with the shieldbug eaten or damaged, but the predator pays a price in discomfort that far outweighs the meal's value. The smell lingers. The taste clings. In some cases, the experience induces nausea or temporary disorientation. The predator survives, but the memory forms quickly. The next time a similar shape appears, avoidance comes before curiosity. Chemical defense becomes chemical education. The shieldbug's coloration reinforces this lesson. Its bright, often metallic hues make it easy to identify. The goal is not concealment, but recognition. Predators learn not just to avoid the individual, but the pattern. Over time, the sight of a shield-shaped insect with a glossy surface becomes enough to trigger caution. The spray does not need to be deployed again. Memory does the work. This combination of visible defense and memorable consequence creates a powerful feedback loop. Shieldbugs that are easily recognized are less likely to be attacked. Predators that learn quickly conserve energy by ignoring them altogether. the ecosystem adjusts. What begins as a violent interaction settles into mutual avoidance. There is a physiological cost to producing these chemicals. The compounds must be synthesized and stored safely within the insect's body, isolated from its own tissues until needed. Specialized glands handle this task, balancing potency with containment. The spray cannot leak or misfire. Precision matters. When deployed, the release is brief, conserving resources while maximizing effect. The Shieldbug does not empty its reserves in panic. It responds proportionally, a measured reaction refined by selection. The visible nature of the spray is not accidental. The mist's appearance enhances the learning experience. Predators do not just feel discomfort. They see the cause. The association between visual form and chemical consequence becomes tightly linked. This clarity accelerates avoidance across the predator population, reducing the number of lethal encounters needed to establish the signal. Shieldbugs often live in open vegetation where concealment is limited. Leaves provide exposure rather than cover, and movement across stems is easily noticed. In such environments, a hidden strategy would fail. Instead, shieldbugs adopt a posture of calm visibility. They walk slowly, rarely taking flight unless disturbed repeatedly. Their confidence is not bravado. It is calculation. The more consistently they are seen and avoided, the safer they become. Predator learning is not uniform. Some species are more persistent than others, especially juveniles that have not yet accumulated experience. These individuals may test the defense, triggering the spray and receiving the lesson firsthand. The cost to the shieldbug population is real, but manageable. Most individuals survive long enough to reproduce, passing on both chemical capacity and recognizable form. The chemical memory formed by predators extends beyond direct encounters. Many animals learn socially, observing the reactions of others. A bird watching a conspecific recoil from a shieldbug may never need to taste one itself. Avoidance spreads faster than the defense ever could through direct contact alone. The spray becomes a teaching tool not just for individuals, but for entire communities. The shieldbug's role in the ecosystem extends beyond predator deterrence. By feeding on plant sap, it influences nutrient flow and plant health. Some species specialize on certain hosts, shaping vegetation dynamics through selective pressure. The chemicals used for defense often originate from plant compounds, transformed and repurposed by the insect's metabolism. The shieldbug becomes a conduit through which plant chemistry affects animal behavior, extending the influence of leaves and stems into the nervous systems of birds and mammals. This connection underscores an important truth about chemical defenses. They are rarely isolated inventions. They are collaborations across trophic levels, borrowed and modified rather than created from nothing. The shieldbug spray reflects the chemistry of its diet, its environment, and its evolutionary history. The defense is effective because it is grounded in the broader chemical landscape of the ecosystem. From a human perspective, shieldbugs are often noticed only when handled, their defense triggering an immediate, visceral reaction. The smell is described as unpleasant, sharp, difficult to ignore. That reaction mirrors the predator experience on a smaller scale. It is a reminder that the defense is designed for vertebrate senses, including ours. The bug does not distinguish between attacker and observer. The message is universal. As the camera lingers, the shieldbug remains motionless, its armor gleaming. The threat has passed. The spray has dissipated. Nothing about the insect's posture suggests fear or exertion. The encounter is over. Somewhere nearby, a predator remembers. The shieldbug's danger is not in what it can physically do, but in what it ensures will not be done again. Its defense is brief, dramatic, and unforgettable. In a world where survival often depends on speed or stealth, the shieldbug chooses reputation. Once established, that reputation does most of the work. Beauty, in this case, is a warning label. The polished shield invites attention, ensuring that when the chemical lesson is delivered, it is tied to a clear visual cue. Predators learn fast because the message is simple. Touch this, and you will regret it. The shieldbug does not need to kill. It does not need to injure. It only needs to be remembered. In the quiet aftermath of the spray, as the leaf settles and the forest resumes its rhythms, that memory persists, shaping future choices. The danger lingers long after the mist has vanished, carried not in the air, but in the minds of those who once ignored the warning. The air around the nest is clear and bright, cut by sharp sunlight that reflects off leaves and bare wood. A wasp hovers briefly at the entrance, body suspended with a steadiness that feels deliberate rather than fragile. Its wings vibrate, not in panic but in readiness, holding position with practiced ease. The insect's body is cleanly segmented, wrapped in bands of yellow and black that appear almost graphic in their precision. Nothing about the pattern is soft or ambiguous. It reads instantly, even from a distance, as something that demands attention and caution. In the visual language of the natural world, few signals are as universally understood. The stripes are not decoration. They are instruction. Across ecosystems and continents, high-contrast yellow and black has become shorthand for danger, a visual code reinforced by repeated encounters and painful consequences. The wasp does not rely on concealment or surprise. It announces itself openly, confident that its message will be received. This confidence is grounded in an efficient and highly targeted weapon, one that does not need to be used often to remain effective. When a potential threat approaches, the wasp's posture changes subtly but unmistakably. The body angles forward. The legs drop slightly, ready to grip or brace. Wings may spread or lift, increasing apparent size and signaling readiness. This is not random agitation. It is a calibrated escalation, a warning before action. Many predators recognize this posture instantly, associating it with previous encounters that ended in sharp, localized pain. The encounter often ends here, without physical contact. Respect is granted preemptively. The stinger itself is a marvel of biological engineering. Unlike the blunt or tearing mouthparts used by many insects, the wasp's stinger is a refined instrument, derived evolutionarily from an ovipositor. It is smooth, flexible, and capable of precise control. When deployed, it penetrates skin with minimal resistance, delivering venom directly into tissue. The venom is not designed to kill large animals. Its purpose is deterrence. It triggers immediate pain, inflammation, and in some cases a systemic reaction that reinforces avoidance. The injection is efficient, conserving venom while maximizing effect. This precision changes the dynamics of predator interaction. A wasp does not need to grapple or overpower. It needs only a brief moment of contact. The cost to the predator is disproportionate to the size of the prey, making the encounter a poor trade. Over time, predators learn that even a single wasp can impose a high price. The lesson generalizes. Similar patterns are avoided, even when the individual insect poses no immediate threat. Warning coloration, or aposematism, works best when paired with real consequences. The wasp delivers those consequences reliably. Its coloration ensures recognition. Its posture signals escalation. Its sting enforces the rule. Together, these elements form a complete system, one that modifies behavior not just in predators, but in the broader community. Animals give wasps space. They alter foraging paths. They learn to interpret the environment differently in the presence of striped movement. The wasp's social structure amplifies this effect. Many species live in colonies, with multiple individuals sharing a nest and coordinating defense. An attack on one often triggers a collective response. Alarm pheromones released during a sting recruit others, escalating the encounter rapidly. Predators that fail to retreat after the first warning may find themselves facing several defenders, each capable of delivering precise injections. This social reinforcement turns individual defense into area defense, extending the influence of the warning signal beyond a single body. From an ecological perspective, this creates zones of altered behavior around nests. Herbivores may avoid plants near wasp colonies. Other insects change flight paths. Even large animals learn to navigate carefully. The wasp becomes an architect of local behavior, shaping movement and interaction patterns through reputation alone. The venom itself is complex, a cocktail of compounds that act on nerve endings and immune responses. Pain is immediate and sharp, demanding attention. Swelling and redness follow, extending the memory of the encounter beyond the moment. In some cases, particularly for animals with heightened sensitivity, the reaction is severe. This variability reinforces caution. Predators cannot predict their own response in advance, making avoidance the safest strategy. Despite this formidable defense, wasps are not aggressive by default. Their readiness to sting is context-dependent, reserved for direct threats to themselves or their nest. This restraint is important. A signal that is overused loses credibility. The wasp's warning remains effective precisely because it is honest. Most encounters end without violence, reinforcing the idea that the stripes mean danger without requiring constant proof. The visual clarity of the pattern plays a critical role here. The contrast is high, the edge is sharp, the repetition consistent across individuals. This makes recognition fast and reliable, even in peripheral vision or poor lighting. Predators do not need to focus to identify the signal. A glance is enough. In a world where attention is divided among many tasks, this efficiency matters. The wasp's movement complements its appearance. Flight is controlled, often direct, lacking the erratic flutter that characterizes many harmless insects. When hovering, the body remains stable, reinforcing the impression of control and capability. Sudden changes in direction are purposeful, not frantic. This behavioral confidence aligns with the visual message, strengthening its credibility. There is a subtle interplay between fear and learning at work here. The first sting teaches through pain. Subsequent encounters are shaped by anticipation. Predators react before contact, guided by memory. Over time, the wasp's influence expands beyond individual interactions, shaping instinct-like responses in animals that may never have been stung themselves, but have inherited or observed avoidance behaviors. The wasp's role in the ecosystem extends beyond defense. As predators of other insects, they regulate populations that might otherwise explode. As occasional pollinators, they contribute to plant reproduction, albeit less conspicuously than bees. Their aggressive reputation often overshadows these roles, but it is precisely that reputation that allows them to operate openly during daylight hours, hunting and foraging without constant harassment. From a human perspective, the wasp's design often evokes admiration mixed with unease. The stripes are striking, almost elegant. The body is streamlined, efficient. There is no excess, no ornamentation without purpose. Every visible element serves a function, from coloration to posture to weaponry. This is design shaped by consequence rather than aesthetics, yet it appears refined because refinement often follows efficiency. As the camera lingers on a wasp resting on a branch, wings folded, antennae sweeping the air, the environment around it feels subtly constrained. Other insects keep their distance, movements slow or redirect. The wasp does not need to act. Its presence is enough. The art lies in this restraint, in a system where form alters behavior without constant enforcement. The danger of the wasp is immediate, but its power is cumulative. Each sting reinforces a lesson that ripples outward through the ecosystem. The stripes remain visible long after the pain has faded, a reminder encoded in memory and instinct. In this way, the wasp demonstrates a fundamental principle of survival. Control behavior, and you reduce conflict. Advertise capability, and you rarely need to use it. The wasp's warning is not loud or dramatic. It is clean, unmistakable, and backed by precision. Beauty here is not softness or excess, but clarity. In the sharp lines of yellow and black, the natural world has drawn a boundary and given it teeth. The result is respect, earned through experience and maintained through design. The web appears first as a distortion, a faint warping of the air where sunlight bends in unexpected ways. At the edge of a forest clearing, strands catch the light and glow with a soft golden hue, stretching between branches like suspended architecture. From a distance, the structure seems delicate, almost ornamental, a fragile lattice woven for beauty alone. Step closer, and the illusion deepens. The silk gleams as though polished, each thread precisely placed, each spiral evenly spaced. The spider at the center waits motionless, legs extended, body aligned with the geometry of its creation. Everything about the scene suggests elegance, patience, and order. What the scene does not suggest, at least at first glance, is violence. The golden silk orb-weaver builds its web not as a passive trap, but as an engineered barrier, designed to intercept movement in open air and convert speed into capture. The placement is never random. These webs are often strung across natural flight corridors, gaps between trees, along forest edges, or near water where insects travel in predictable paths. The spider reads the landscape as a three-dimensional map of traffic and positions its web where the probability of collision is highest. The air itself becomes territory, parceled and claimed by silk. Golden silk is not merely strong for its thickness. It is strong in absolute terms. Pound for pound, the material rivals high-grade steel in tensile strength while remaining far more elastic. This combination is critical. When an insect strikes the web at speed, the silk does not snap. It stretches, absorbing kinetic energy, dispersing force across the entire structure. The prey is slowed, entangled, and held fast in a fraction of a second. Escape attempts only tighten the grip as vibrations trigger a rapid response from the spider. From the spider's perspective, the web is an extension of its sensory system. Each strand transmits information, subtle changes in tension and vibration mapping the exact location, size, and struggle of whatever has collided with it. The spider does not need eyes to hunt effectively. It reads the web the way a musician reads an instrument, interpreting frequency, rhythm, and intensity. A small fly produces one signature, a large beetle another. Even wind has its own pattern, familiar and easily ignored. The golden color of the silk is not incidental. In sunlight, the threads reflect wavelengths that blend into the visual noise of foliage and glare, making the web difficult for flying insects to detect. Many insects navigate by polarized light and contrast. The silk exploits this, reducing visibility while maintaining structural integrity. The web does not need to be invisible to all prey. It only needs to be invisible long enough. When impact occurs, the transformation from beauty to brutality is swift. The spider rushes forward, wrapping the prey in additional silk, immobilizing wings and limbs before a bite delivers venom. The venom does not kill instantly. It subdues, liquefying internal tissues so they can be consumed later. The web becomes both prison and pantry, storing meals in place until the spider is ready. There is a hierarchy within the web itself. Stronger radial threads bear the load, while spiral threads maximize capture efficiency. Damage is inevitable, but the design anticipates it. Portions of the web can fail without compromising the whole. Repairs are constant, woven back into place each night or morning depending on conditions. This maintenance is part of the spider's daily rhythm, an investment in future success. The female golden silk orb-weaver, often significantly larger than the male, dominates this architectural space. Her size allows for greater silk production and the handling of larger prey. Smaller males may linger at the periphery, navigating carefully to avoid becoming accidental meals themselves. Even within the species, the web defines power dynamics, dictating access and survival. The ecological impact of these webs extends beyond individual predation events. By capturing large numbers of flying insects, orb-weavers influence local population dynamics, reducing pressure on plants and altering competition among insect species. The web becomes a regulatory force, shaping who thrives and who does not within its reach. Birds and larger animals learn to recognize these golden barriers, adjusting flight paths to avoid entanglement. The web teaches caution through experience, much like chemical defenses or warning colors. There is an irony in how often humans admire these webs without fully acknowledging their purpose. Photographs celebrate the symmetry, the glow, the craftsmanship. Yet every strand exists to intercept life in motion. The elegance is functional. The symmetry is optimized. Nothing is wasted. The web is not art for art's sake. It is a solution to a problem posed by evolution: how to capture fast-moving prey without chasing it. Unlike predators that rely on speed or stealth, the golden silk orb-weaver lets the environment do the work. Wind carries insects into the trap. Light disguises it. Physics completes the capture. The spider intervenes only at the final moment, conserving energy while maximizing return. This efficiency allows the spider to remain stationary for long periods, reducing its own exposure to predators. Even the web's visibility at certain angles serves a purpose. Larger animals that might destroy the web entirely can sometimes see and avoid it, preventing catastrophic damage. The spider does not benefit from catching prey it cannot subdue, or from rebuilding a web destroyed by a careless collision. Selective visibility balances risk and reward, another layer of refinement in the design. As dusk settles, the golden threads fade into shadow, and the web becomes harder to see even for human eyes. Nocturnal insects emerge, guided by faint cues and internal clocks. The web remains, ready. Each night is an opportunity. Each dawn reveals the outcomes, wrapped and waiting. The golden silk orb-weaver does not pursue prey. It does not threaten or warn. It builds, waits, and wins through preparation. Its beauty lies in precision, in a design so effective that it reshapes the space around it. Air, once free, becomes contested. Movement becomes risk. As the camera pulls back, the web fills the frame, glowing softly against the darkening forest. It is undeniably beautiful, but beauty here is not kindness or grace. It is efficiency rendered visible. In nature, the most refined designs are rarely neutral. They exist to solve problems, to secure energy, to persist. The golden silk orb-weaver's web is not a decoration suspended in the forest. It is a weaponized landscape, a triumph of material science and spatial strategy. And in that quiet, gleaming structure lies a final truth. The most beautiful designs in nature are often not meant to be admired. They exist to win.